All right, cool. So we are now recording. So as I said, any questions about the characterization assignment or project before we move forward with the lecture?
I have a few.
I have a few as well.
Okay, yeah. Karthik, go first, and then Baji, I think it was you. You will go to your stuff after.
So for the TLM and CTLM, I checked my calculation and rechecked my calculation. The sheet resistance is still like really large for TLM compared to CTLM. I am starting to assume that probably it's because there's something wrong with the wafer. I'm not sure, but if others can pitch in, or they can, if they have like a similar kind of error, probably, I don't know.
Yeah, I was ready to assume that we should expect the sheet resistance to be roughly the same between the two structures, but I have one that's twice as big as the other, or something similar.
Okay, so both of you guys, if I'm understanding correctly, have a result where one, either the TLM or the CTLM, is coming out to be larger than the other. Which one is larger for both of you? Is it the same structure?
I'm pulling up my results.
Yeah, me too.
It should be similar. So, and if you're seeing a factor of 2, that should be very suspicious. So you should look at closely what you've got going on there. There might.
I'm ready to be suspicious.
I can add one comment. Actually, normally TLM is more preferred. CTLM may have some current crowding because you have a circular structure and current is coming from or going out from the Schottky to ohmic or ohmic to Schottky. So I have seen some paper where people have reported that maybe CTLM may not give you accurate value, and that's why I guess TLM is more preferred in. But the problem with TLM is that you need to make a MESA, and then it will take more steps fabricational in comparison to CTLM, because there you just put contacts and it would be easier. So I won't worry much if it's not very big, kind of like an order difference. If it's 2 times, 3 times, I would say maybe it's fine.
I actually don't think it should be that big of an error, and there should be a correction factor that you can apply to the CTLM that helps improve the result a little bit. So while you guys are discussing which of the structures you have, I'll also open up my data. It should be pretty similar. I don't think I got a factor of 2 difference.
The TLM is twice as big as the CTLM.
So you are getting TLM higher than CTLM.
That's roughly what I have as well. It's a little bit more than 2 times. Well, no, it's a little less than 2 times for me.
Okay. So how about Karthik? For you, is it also about a factor of 2?
Yeah. So it's around like 1.6 or 1.7. If you want the exact number, I can pull it up. But yeah, it's like around 1.5 or to 1.6. The exact number is 5. Yeah, it's around 1.8 times bigger than the. So the TLM is 1.8 times CTLM. The sheet resistance.
Okay, and what is the sheet resistance value that you guys are getting in each case?
So I haven't redone my calculation. I used the resistance value which is given in each sheet, and the sheet resistance for TLM is 543 ohm square, and for CTLM it is 288 ohms per square. Yeah.
Okay, I think based on what I got, I would say that your CTLM value is closer to what you should expect for both structures.
Okay.
So your I might be getting these mixed around. It's just be more clear if I didn't get mixed up. It's the value that's in the 500s.
Oh, okay.
Yeah,
So
was that the TLM or the CTLM?
It was the TLM.
Oh, the TLM. Okay, the TLM value, the one that's in the 500s, is the one that you are getting correct. The CTLM, it sounds like maybe you've overcompensated somehow. That's a bit too low, the 200 something that you got.
Okay, so let me recheck the calculations again.
Has anyone else tried this yet and actually gotten 2 values that agree with each other?
I haven't gotten that far yet. I'm in the process of doing it though.
Okay. All right.
So I can answer that later today, probably.
Sure. Why don't we do this then? For Baji and Karthik, could you guys go to Moodle after class and post the values that you got in that? I think I put a section. There's like a project, forum or Q&A type of section. If you could post the values there and kind of poll the class, and then if you'd like, you can also send me your spreadsheet, or if it's possible even to upload it to Moodle, you can upload it to Moodle, and I can take a look at it and give you feedback. I have a sneaking suspicion that there's just a divide by 2 type of thing that's missing in one or the other case. Probably on the CTLM case, there's probably, you maybe divided by twice more than you should have, or multiplied by twice or something like that.
Yeah, I can do that once the class gets over. So my another question is, so for the width normalized contact resistance, should we like multiply by the width of the contact or divide? Because in some cases the unit is given as ohm millimeter or ohm micrometer. So are they multiplying or dividing for the width normalized?
If it's a ohm millimeter, then you should be multiplying. I think usually it's like an ohm centimeter squared is the specific contact resistance unit that I tend to see. So there are some equations that I think I put I cited in the Schroeder book that give you exactly those values. If you do those things, you should be able to get those. But yeah, check your units, absolutely. And for specific contact resistance, your unit should be ohm centimeter squared or ohm meter squared. Ohm centimeter squared would be the more, I guess, common unit to use.
Okay. And for the FETs, so I was able to make sense of the other characteristics. So there were 2 things which I couldn't like understand why it was there. One was the transverse stress test and the dual sweep. So
okay, those are tests related to the stability of the device, both the dual sweep and it should be transient. Is it transverse or transient?
It says transfer, but I assumed looking at them that there's probably some time interval associated with each data point, but it doesn't have a settings to sort of tell you what that time interval is. Granted, if it's fixed, it may not matter.
Right. Let me just pull this up again, the folder. So you guys are referring to transfer stress test, right?
Yes.
And then dual sweep.
Yes.
Okay, yeah. So both of those are 2 different types of tests that one can do to look at stability of the device. Look at those carefully and try to look at the literature to try to understand where those things are coming from. But stability of the device, specifically at the interface between the semiconductor and the dielectric, would be causes for those tests to look the way that they do. And to answer Baji's question about intervals in between, you're right. I don't think I provided time intervals in between. It's okay. You don't need to know that for the purposes of this report. You can just assume that using the run number that they were done in that sequence. So 285 was done before 286, which was done before 287. And using that sequence, you should at least be able to derive an understanding of what direction the curves are changing.
Right. But I meant, would we need to know a time interval in between measurements on a given run?
Yeah, I think in an ideal world, yes, you would know that. But for this particular case, you don't need to know that. You can just assume that they were done one after the other and that it resulted in some sort of change.
Okay.
Sorry about my daughter making her little squeals in the back.
She's allowed to be there. It's her house.
So yeah, those are my questions. I'm good. Yeah.
Okay, cool. Any other questions?
Mine had mostly overlap. I was getting a little tripped up by the units with normalized contact resistance and specific contact resistivity, and I wanted to make sure I was keeping track of my units right. So, but we discussed that a little bit.
Yeah. Definitely, compare your numbers. So for example, most papers out there that talk about contact resistances are specific contact resistance will give the value in ohm centimeter squared. So you can compare your number against those and at the very least see whether you're within an order of magnitude of where those results are. If you are more than like 2 or 3 orders of magnitude out from that, then you can probably assume that something is wrong with your calculation. But that's another one of those things that I'm happy for you guys if you want to post some numbers on Moodle and we can all kind of compare and I can look at your spreadsheet and give you some feedback. That might be the best way to handle that since it might take a little bit of time to go through it.
Sure. And just as a quick clarification, when you ask for the width normalized contact resistance, that's distinct from the specific contact resistance because you're only multiplying by one of the dimensions of the contact?
You are correct. Yes, absolutely. Width normalized, like you said, will only be with respect to the width. So it would be like ohm meters or ohm centimeters or ohm microns. And then the specific contact resistance takes into account the area, which will incorporate the width, but it will also incorporate a length. And maybe pop quiz, what length do you guys anticipate that being?
Right. And then
a quick question. I mean, what do you think it would be though? Because that's an important thing to know if you want to calculate the area. You know the width, but what will the length be?
It should be the transfer length, correct?
Perfect. Yes, exactly. So you'd have a rectangular area underneath your contact defined by transfer length as the length, and then the width of the contact. Yep.
Yeah. So yeah, and then about the transfer length. So I was basically wondering, like, do anytime we're trying to normalize any of these measurements, we should be using the transfer length for dimensions as opposed to the entire contact area.
That's right. Yes. And so for the rectangular TLM, it's a simple rectangle. For the circular TLM, it's a bit more involved because you are working with circular structures. So you're going to have to think about a donut shape.
Right. Classic geometry.
Yep.
And this is just a curiosity for myself, but the sheet resistance that we're measuring specifically applies to the interface, or is it some other area?
No, it applies to the material, the semiconductor in between the two contacts that you're measuring current across.
Okay. All right. Yeah, I was getting tripped up on visualizing that, so I wanted to clarify that.
Yeah, that's why it's the slope of that line that you're drawing, and so the slope should stay the same, right? Because the material that you're placing your contacts on should be the same, but the further apart the contacts are, the actual resistance that you're getting will be different.
So does that mean that the slope between our CTLM and TLM measurements, they should be the same? Or approximately similar?
It'll be very similar, yeah. After correction and everything, it'll be pretty similar.
Okay, so that's probably our issue because my slopes are very different. About the way the correction is supposed to work, when looking at the book, applying the correction seems to move the measurement points upward on the graph, but because my correction values are all less than 1, they reduce it. So am I doing that wrong?
Okay, so I should say something actually. With regard to the statement I just made a second ago, there is a correction factor that is, let me just check here. It should be like a 2 pi kind of correction factor. So you should expect about a 2 times kind of change on the slope. So your slope, in other words, if you just take the slope of the CTLM and you compare it directly to the slope of the TLM plot, it will not be the same. You do have to multiply it by like a 2 pi kind of factor.
Yeah. I think that I believe I'm doing that to get my L, or to get my sheet resistance.
Okay. Why don't you send me or post on Moodle your spreadsheet and I can take a look?
Sure.
Sorry, she's getting excited. Every time I talk, she likes to get in the middle of it.
But yeah, she's excited about contact resistance.
Yeah, it's an exciting topic, even for a 5-month-old.
If we're taking too much time with this, we can do that.
Yeah, I was thinking I want to make sure Dollar has enough time to get through his slides, but I want to also answer this question because it's an important detail. So why don't you post the spreadsheet on Moodle or send it to me, whatever way works, and then I'll take a look at it and compare against my own calculations. I think you guys are very close based on the numbers that you're giving me. It just sounds like there's a little bit of a correction factor somewhere in there that we have to fix.
Okay.
Cool. Any other burning questions before we get into Dollar's lecture? Okay, awesome, cool. So Dollar, I will let you take over. You should have the ability to share your screen. Dollar has planned like some slides on characterizing Schottky diodes, which are important for power devices and also form the gate, as you guys know, of the AlGaN-GaN-HEMS. So he's got some slides that kind of explain how to do the characterization, how to pull out important parameters from all of that. And hopefully if we have time, he also has a plan to show you like a live demo of some examples of how to plot data and analyze it. Maybe what we'll do is, if we do get to 2:45, then if you guys have like another class or something and you need to step off the call, you can just drop off. But we'll probably just keep on going as much as we can and record it. Yes, we'll record it, and then that way you guys can see it as well afterwards. So, Dollar, without further ado, take it away. Thank you.
Okay, thank you. So let me share my screen. Okay. I guess everyone can see the presentation.
Yeah.
Okay. Let me move this somewhere. Maybe I just, okay, minimize it. Okay. So today I will discuss about how to characterize a Schottky diode. And during the talk, I mean, if you can ask me a question whenever you feel so in between, so I don't mind, because then we can discuss more and maybe you will understand better. So no problem. I mean, I would say if you have any question, ask me in between. So before moving to a Schottky diode characterization, first I want to discuss like where those devices are used. So here is an example that let me also open it. Yeah. So here is an example that I did in one of my power electronics course that I designed a 400-volt electric vehicle charger. And from the circuit, we can see there are a lot of devices, power devices like diodes that we have in many places, and we have transistors. And the main requirement of the circuit was that we have a certain input power, and then we convert or we boost that power to charge the electric vehicle. And from this red circles, you can see there are many diodes. And mostly it's preferable to use Schottky diode because they have a very low turn-on voltage compared to the PN diode. And because of that, we will have a lower power loss. And also because these are unipolar device, meaning only electrons will flow when the device is on. And because of that, now you can turn it off very fast. And because of that, we can increase the overall frequency or switching frequency of the circuit. And that will allow us to reduce the size of inductor and capacitors are used in this circuit. And because of that, if you have a smaller inductor and capacitor, the overall area of the circuit will reduce, and also it will be lighter if we increase the switching frequency. So the point here is that the Schottky diodes are very useful in power application for power conversion. And there are many materials that use, for example, silicon carbide, silicon, gallium nitride. And here is an example of a silicon carbide Schottky diode fabricated for 1000 volt. Here is a schematic cross section where we can see that there is a Schottky contact on top and then ohmic contact at the bottom. And for Schottky contact, we can use different metals such as nickel or platinum. And based on the work function of the metal, we can have a different barrier height. And here is an IV, room temperature IV in a log scale, where we can see the on current will increase after certain threshold voltage or a barrier height. And then in reverse bias, we can see that devices are, they are shown till 1000 volt in both cases for nickel as well as platinum. And from here, we can see what is the leakage current and what is the ideality factor. Usually we want ideality factor as much as close to 1. And then from CV measurement, we can see that now we can have barrier height we can find from this intercept, as well as from the slope we can find the doping that is used to make this device. And they also did a temperature dependent measurement where with higher and higher temperature current goes up, and using this temperature dependent measurement we can find the barrier height as they did here. And for nickel they said okay, the barrier height they found is 1.37, and for platinum it's around 1.15 eV. And similar efforts are done in also GaN HAMT Schottky diodes, where you can see there is a schematic cross section where they etched the UlGaN and then made a contact or Schottky contact to the GaN. And for ohmic, they have a regrowth and then they have a ohmic contact. And for a better breakdown voltage, a better edge termination, they have also used field plate. And here is then a room temperature IV, where we can see the ideality factor is around 1.2. And they use different separation from anode to cathode. And for that, they have plotted a linear where we can see the resistance changes. Larger the separation, the resistance will be higher. And you can find the on resistance or a specific on resistance from this graph, where some people directly just use the current and voltage from a given point, and mostly they say at 100 milliampere per millimeter, and then from there you can find a resistance. Or you can also take a slope of this graph, and from there also you can say what is your uh, series resistance of your device. And they also did the reverse bias breakdown measurement for all different cases, and they found that the higher the distance, as we know, will have a larger breakdown voltage. And from their simulation, they found the maximum electric critical field or maximum field they achieved in their devices around 1.5 megavolt per centimeter. And here is they compared their device results with compared to the gallium nitride material or theoretical unipolar limit, and they are very close to the material limit. So one can fabricate a diode, let's say directly on GaN, then why to use even UlGaN GaN? Because here they are still making a contact to GaN. But then here they can have an advantage of the two-dimensional electron gas. And we know from this course that the mobility of the 2DEG density is higher than compared to the gallium nitride bulk mobility. But the problem here would be the better edge termination, because of we can't have a better edge termination compared to the conventional GaN, and because of that you would get premature breakdown. And we can see from this graph that electric field is only reaching to 1.5 megavolt compared to in GaN the maximum theoretical critical field is around 3.7 or 3.8. So the main advantage here to use this UlGaN GaN HAMT is to have an advantage of 2DG, and because of that you can have a low on resistance. People also have done the Schottky diode fabrication on pure GaN on GaN material, and here is one example where they have made a contact on GaN grown via AP on GaN substrate. And here is a room temperature IV that they did, and from that they extracted the turn-on voltage, which is around 0.69, and at higher voltages the current reaches to compliance. And from log plot of this current density, now we can find a barrier height using this equation, where we need to put a Richardson coefficient. And I'll discuss all of this in upcoming slides, how to do all this thing. But here I'm just giving you an example that people have done this, and this is a standard way where they characterize the material via doing different measurements like IV. And also they did CV measurement. From there they found the doping, and I will show how to do that also. And for this devices, they showed the breakdown is around 1200 volt. And probably because they didn't use a better, didn't use any edge termination, the device got early breakdown compared to the actual, because we can see that even another device has very similar very similar breakdown voltage, but the resistance is still lower. So all of this, the reason to show all of this graph is that how to do the characterization, how to get all these different parameters that are used for different application, and then you can target particular application based on the values. So First of all, I want to show you how metal and semiconductor junction works, how band diagram looks. And here, let's say we have a N-type semiconductor, and then there is a metal that we place, which is a Schottky contact. So if both are separate, let's say initially, then we can see a metal will have a Fermi level, and then it will have from a vacuum level, there would be a work function for each particular metal, and different metal can have a different work function. And for the N-type semiconductor, we can see that the Fermi level would be closer to the conduction band. And then from the Fermi level to vacuum would be a work function for the semiconductor. And from the conduction band to vacuum level, we call it electron affinity. So now when you put the metal in contact to the semiconductor, then based on this Fermi level difference, the barrier will be created, and the barrier height would be the difference between the metal work function and the electron affinity of the material. And after that, the barrier gets created. There would be a depletion layer inside the semiconductor, which is called a space charge layer or a depletion layer. And to understand how this forms, then I would say a very easy technique is that you can see there is a Fermi level difference, and now you can see that if the Fermi level needs to be aligned, the semiconductor needs to give some electron to this, and when it gives some electron, then there would be a positive charge left behind, and that will create a depletion region. So that's how we can remember that, okay, when this needs to be aligned and this needs to give some electron to this metal, and that's how the Fermi level gets raised, and then you can have a barrier and then a depletion region. Similarly, for p-type semiconductor, if we have, and if you put a metal contact, before putting a metal contact, then it's the same, then the Fermi level would be now closer to the valence band, and the work function will be higher. And if we align this, then now the barrier will be in the reverse direction compared to this, and now hole can't go up, and we will have a barrier, and that barrier height would be again it would be same as the 5m minus chi electron affinity, and then you will have a depletion region or a space charge region in this semiconductor. So after this, let's say now if we apply a positive voltage or negative voltage to the metal, and how current will flow. So if I apply a forward bias or a positive voltage to the metal, then based on this equation, now you can see if I apply more and more voltage, this will go up, and then the barrier will get reduced, and now electron can easily move from a semiconductor to the metal, and then we will get a current. Whereas in the reverse bias, when we apply more and more voltage in a negative to the metal, then the band goes down, and then we can have a larger and larger barrier, and electron can't go up. But then there would be some electron which will go either by a tunnel or from the barrier, and that will give us a leakage. So from this diagram, now we can see that in a linear scale, in a forward bias, the current will go up once the barrier, once the electron can cross the barrier, and then we can have some current. And ideally, it should go like this, but in real life, because now we have a bulk material, that will give us some resistance, and that's how we can find a series resistance. And in a reverse bias, because electron can't go up from this side, but electron can go from this side, and that will give us some leakage current, and that will be given like this. And so now then I would like to show how we can derive an equation from using the electrostatics, and that will then predict how much current we will have based on these parameters. And this is the equation for the current, where we have IS is a saturation current or a reverse leakage current that is fixed. And based on this voltage, now we can have current increasing exponentially. And the equation for IS can be given as this, where we can see that we have a star, which is Richardson coefficient. And based on your barrier height, you can find the leakage current. So mainly there are many parameters that needs to be identified using this IV or as well as CV also. And the main parameters are barrier height, what is the threshold voltage, the rectification ratio from on to off, and then the series resistance, what is the leakage current, and if we are making power device, and what is the breakdown voltage that we can get from the device. And also from CV we can find the doping, and as I said, to find these parameters we need to do room temperature IV measurement, room temperature CV measurements, as well as temperature dependent IV measurement. And so let's say you want to make a power device and you ask a material grower that can you grow a material for me, and he gives you some material, and now your task is to figure out whether you really have that particular doping, and also what would be the barrier height if you use certain metal. So for that you go to the lab and you fabricate, let's say, a lateral diode where you can easily, and it's faster to make, and then you can from this structure you can easily find barrier height and doping. But if you want to also find a breakdown voltage, then this is not a good way to fabricate the device. And instead, what one would do is that either you can make a quasi-vertical so that you can find a breakdown for this material at what voltage you can break down. And if you have a substrate, then you can directly fabricate a vertical diode, and then you can have a breakdown voltage measurement on top of. You can also do the same, all of the same extraction that we do in lateral. But to do the background voltage measurement, we know that we also need a edge termination, because if you don't have, then you will get a premature breakdown and you may not get the actual breakdown limit of the particular material. So let's say you went to lab, went to the clean room and you fabricated the structure. And now you go to the characterization lab and you want to measure IV and CV and other, you want to extract all the parameters. So I will show in one by one. So let's say you go to the lab and you connect a ground to the ohmic, and then you apply positive or negative voltage to your Schottky. And then you will get a data a spreadsheet that Dr. Beverly showed previously also. And then you get a current and voltage based on whatever you apply. And then from this current, now you can plot a current density according to that, because now you fabricated, you know the area of this diode, and based on that area, you can normalize the current to get a current density. And then you can plot from -1 to 1, whatever you measured here. And from this graph, now you can see that from this region, we can find a slope. And from the slope, we can say, okay, the sheet resistance of this device, of this material, is this particular value that I found from my IV. And to get a threshold voltage, now I can take a straight line from this resistive part, and I can say, okay, the device has threshold voltage around 0.4. And for power application, actually, the lower threshold voltage is better. But then from this equation, we can see a threshold voltage, or let's say a barrier height, can give me, if I have a lower value, then the leakage would be also higher. So from these measurements, we can find series resistance, we can find the threshold voltage. And then now I will show, so if I plot the same graph that I had here, if I plot in a, this was in a linear scale, and if I plot in a log scale, so I have now log scale in the y-axis and the same linear axis, then I can see what is my leakage, because from previous graph, I can't see what is the leakage. Here I can see the leakage is increasing when I'm applying more and more reverse bias voltage. And from this graph, now I can find a rectification ratio that let's say at +1 and -1 voltage, what is the ratio. And from this graph, I can say, okay, this is the value that I can get from this measurement. So normally, when you have a lower leakage, you would get higher and higher on-off ratio. And you may see in a lot of literature that people compare the on-off ratio for their devices compared to the other. And they say they have a better than other. So this is a one way where you need to make sure also that you are comparing for a particular when the device is on, and with respect to the whatever voltage you choose here, you can choose the same voltage and you can say, okay, your on-off ratio is this. And in some of the literature, they compare the on-off ratio from where the device is totally on and to when they are reaching to the breakdown, or let's say around, if your device is, can have a capability of 600 volt, then they compare around at 500 and they say from +1 to 500 is rectification ratio is 10⁻², 3, or whatever the value they get. But then what another thing we can see is that the leakage is very high for this device that I made for n-polar GaN. And there are a lot of non-idealities that we will get during the fabrication also, and there can be some non-idealities in your material quality, such as dislocations, and because of that you will have higher leakage, and because of that you will have lower on-off ratio. And that's what people compare in different literatures, that someone claimed that, okay, I have a better material quality, and then because of that I have a better on-off ratio. So this is just, I wanted to give you a comparison and that you can have a better understanding. So as I have derived showed the equation in previously, where we had I instead of current, now we can also have a current density, and that can be given like using this equation. And if I take log on both sides, then I can have this equation where
linear equation.
sorry.
No, we'll have a linear equation and we can plot.
Yeah. So my intention here is to find ideality factor, the n, and what is the leakage current. So if you take a log, then this equation looks like a line equation, where y is equal to c plus is the intercept and the slope, and this is the slope from where we can find n, and then from intercept we can find what is the leakage current at let's say zero bias. And this is the same graph that I plotted only in forward bias. And now if I draw a straight line, then the slope of that line will give me the slope, and meaning I can find the ideality factor, and the intercept where it to the zero will give me the leakage current. And from this graph now I can find the ideality factor is 1.13 and leakage current is 3 milliampere per centimeter square. And as I said, normally ideality factor, we want a 1, but because of a lot of non-idealities that come during the fabrication or even some material quality, will give me the higher ideality factor. So people compare their devices with the other and claim if they have a better ideality factor or not. So this is a way where we can find these two values. And from IV measurement, we can also find a barrier height, which many people do. And for that, now we have a value of JS, and then we have value of, so we need a value of A star, because now at room temperature, we know T, so we can find the barrier height. And for that, as I said, we need this A star, and there is some equation based on that. You need some theoretical values, or there are a lot of experimental values that people have found. So if you put those values from other literature, then it can lead to have a wrong IV barrier height calculation. So the main, other method to do IV measurement, barrier height measurement, is to use a temperature dependent IV. And I'll show in the next slide how to do that. Another thing, if I want to find a background voltage, which in my devices I didn't do, so I had a schematic where I took it from internet. And it's very easy to find background voltage when you can see a sudden rise in the leakage current will tell you where your background voltage is. So then, as I said, now we can, instead of using the IV barrier height, room temperature IV measurement to get a barrier height, it's better to use a temperature dependent. And for that, now I can temperature dependent measurement on the same Schottky diode that I showed before. And then when I increase the temperature, current will go up. And based on this equation, if I take T squared down, and then now I can have JS for each cases, and I can take it from this line, and then I can have all the values. And if I take ln of this graph, then I can have again the same line equation. And from this I0, I can plot a graph where I can have ln JS by T square is this, and then that is extracted from this, and based on each temperature I can make these points. And when I plot it, and then now you can see we have a very straight line, and that line of the slope of this line will give me the phi b. And if I take an intercept where this reaches to 0, then I can also have a star. So I can see, then I can compare my A star with the literature also, whether I have a same or different. So instead of using from literature, the good method is to use a temperature dependent measurement, and from there you can find the barrier height. And as I say, I found from here, now my barrier height is around 0.4, and I can see I have a temperature independent barrier height. So I can also show you what would be inhomogeneous barrier height, where you can see now with temperature, my barrier height is changing. So there are many literature where you will see a straight line and then people claim they have a temperature independent. And if you have some non-idealities either in material or during the fabrication, you can see sometimes inhomogeneous barrier height also. So then now I would go to the CV measurement that I did at room temperature. So here is the same Schottky diode that I have a metal and then I have an N-type material. And now if I change my reverse bias voltage with a given frequency, then I can, when I increase the reverse bias voltage, I will get more and more depletion, and then W will increase. And here is the equivalent circuit where I can see that based on this W, now I will get a capacitance. And that would be this, and then I will have some resistance of this layer, and there would be some conduction also, and which will be modeled as G. And you can, when you do the CV measurement, this model you have to put into whether you want to use parallel, or there are also some series model, but usually we use the parallel model. And from that, now we can see that the equation for the capacitance is this, where W we can replace with this equation, where we can see that if you increase the reverse bias voltage, you will get more and more W, and because of that you will get smaller and smaller capacitance, where you can see here that at zero bias you have a certain value, and then when you increase the reverse bias voltage, the capacitance will go down because the W is going up. And from this graph, let's say from this equation, now if you rearrange this equation in a way that you can get a line equation, and from that you can now have a slope. So if I plot 1 by c square or area by c square graph using the same data, then I can have a straight line, and the slope of this line will give me a doping. And that's how I found the doping from the slope of this graph. And I also, from this equation, we can see when A by C square reaches to 0, then I can say V is equal to your VBI, or the intercept voltage would be your VBI. And from the Venn diagram, we can see that from VBI now you can find phi B. And so that is another method to find the barrier height using a CV method. And that will need intercept from the positive axis. And there is also EC minus EF, and for GAN, actually the doping at 7E17, you will have EC minus EF less than 0.05 eV. So whatever value you extract from here, you can say that is your barrier height, and it is 0.6 eV. So now let's compare the barrier height that we found from IV and CV. And from IV, from temperature dependent IV, we found the barrier height is 0.4. Whereas in CV, we found a barrier height 0.6. So we can see there is a difference between the IV and CV. And usually this difference are because of a lot of non-idealities in the measurements, or actually in the devices. Such as in IV, you see there may be some tunneling components. So because of that, you actually measure lower than what you actually see, what you actually have. And the other non-idealities, such as like you may have non-ideal barrier or non-uniform barrier, and then there are some metal-induced gap states. And because of sometimes rough surface, you see different field crowding, and because of that, you can see different barrier height. And also, normally in CV, the extra barrier height will come because of the presence of native oxide. And I will discuss few of this in upcoming slides, so then you can have a better understanding. So first, I want to discuss a non-ideality in IV. So there is the image force lowering and also the tunneling component. Here is the schematic of the Schottky diode. And then, so when electron comes near to the surface, there would be image charge will be forming in the metal. And because of that, now instead of having this barrier phi B, because of this field created near the junction, that will reduce the barrier, and that barrier would be, the reduction would be delta phi B. So actually when you do IV measurement, you don't see the actual barrier, you see the phi B minus delta phi B. So what I'm saying is that, and you can calculate actually how much would be the barrier lowering, and that would be you need to find how much would be the electric field near the surface when you have, let's say, 0 voltage. Then from this equation you can find, based on your barrier height, what would be the maximum field, and from that field you can find the delta phi b, and then from there you can say, okay, my actual IV barrier would be slightly lower than what it should be. And so now if I want to find how much barrier height lowering I have in my devices, I can use that VBI I found from CV, and then I can find, let's say, delta phi b is around 0.07. And if I use VBI from my IV, then it's around 0.06. In short, the maximum barrier height lowering would be around 15 to 20% of the value that we get either from CV or IV. So let's say my actual barrier was not 0.4, but it's 0.47, but it's still lower than the CV, which I got from CV. So that we will see in the next slide why we see a higher barrier in CV. Another thing, because of this image force lowering, we have seen this IV in previous slides, that we can see from this equation that we had before. If we say that if I have a barrier height, let's say 0.5 or 0.6, then I should have a constant leakage such as this blue graph. I should not have leakage increasing, right? Because the equation doesn't show me that any voltage dependence. But actually what happens in the real life is that because of this electric field, when you apply more and more reverse bias voltage, the field will go up, and because of that the barrier lowering will be higher and higher, and because of that now you see the phi b reduces with reverse bias voltage, and because of that you see more and more leakage instead of constant leakage. And there is another parameter also, which I said, which is a tunneling, because when you apply more and more reverse bias voltage, the band goes down, and then this region gets thin, and now electrons can get easily tunnel. So the modified equation for the reverse leakage is this, where we have a certain leakage around it, let's say 0 bias based on this, and then from the barrier lowering, there would be additional leakage, and because of the tunneling, the field will increases in reverse bias, and you will have more and more leakage, and that's why you see a line going upwards rather than having a constant leakage. So this is all about non-idealities in IV, and so now we'll see why we still don't match the CV barrier compared to the IV barrier. So then, as I said previously, that when you measure CV measurement, when you do a CV measurement, if you have a interlayer dielectric, so ideally from the previous slide, we wanted to see a barrier around 0.47, but instead of that, now the graph is having a higher a lower capacitance, and because of lower capacitance you will have a line going like this, and then you will have a higher barrier. So as I said, if we have an interlayer dielectric, then we can model that, and we can actually find that how much would be the difference. And from here you can see that if I put this interlayer dielectric in between, then when I apply a reverse bias voltage, the equivalent circuit changes, and because of that now I have an additional capacitance coming from the interlayer, and then because they are in series, the overall effective capacitance would be lower, and because of that your 1/c² would be higher, and that's why it shifts up when you do a measurement, and then that will give me a higher barrier compared to what I should be seeing. So that's why the interlayer dielectric changes the barrier height. And another thing also I wanted to talk is that now let's say if you have a trap charges in your bulk. So when you apply reverse bias voltage, the depletion region grows in this direction. But then if you have some trap charges, either positive or negative, when you do a CV measurement, you may not get a straight line because your doping is changing once you see some trap charges. So effective doping would be different. So then the slope won't be the same as it should be for ND. Now you have a inclusion of ND and NT, or the trap charges. So that is why you see a difference in the CV in 1/c² versus voltage. And we can also, so all of this measurements still are showed was for gallium nitride only. People also do a CV measurements to find sheet carrier density for AlGaN-GaN HEMT. So let's say here you have a cross section and then you made a Schottky diode, either circular or different geometries, and then at zero bias you have a two-dimensional electron gas. And then so here is the schematic of the fabricated device, or the microscopic image of the fabricated device, where we have a Schottky inside and ohmic outside, and you go to the lab and you apply voltage, negative voltage to the Schottky, and then you can have a CV measurement like this. And after it crosses to the pinch of voltage, now you will deplete all the 2dG, and because of that you won't see any capacitance. And now if I integrate this graph, because if I do C into dV, that will give me a charge, and then if I know the area of the diode, then I can find a sheet carrier density as a function of voltage. And you can see at zero bias now you have around 6 into 10 to the 12 centimeters per centimeter square sheet carrier density. So using this method, will report how much sheet carrier density they have in their devices. With that, now we can plot some data, and this was the slides that I had. Any questions first? Data.
Yeah, thank you, Dollar. That was really good. I think I agree. This is a good opportunity to ask questions if anyone has some before he switches over. But these are some amazing slides, really nice figures.
Yeah.
Anyone have any questions for Dollar?
I have one. So why do you think the phi B value from the CV measurements are better than phi B values from the IV measurements? Is it like the non-ideality is more over there?
Normally, the CV measurements give flat band condition, meaning you will get the barrier height of this flat band, the condition, without the barrier lowering. So it's not about better or worse. Normally, you do IV from the IV measurement, because normally you are doing from a circuit application, you are passing a current, you are getting some current, and for that you normally will see an effective barrier. So in actual application, you will see this barrier other than this barrier, but this is a way where you can see what is your flat band condition or what is your actual barrier, and then based on the chart image force lowering, how much would be the reduction. But actually in your device, you will be seeing this barrier only. And on top of that, you will actually see what is your threshold voltage, because then you can have an idea, okay, where is your device is on and when you want to off the device, and what is the limit and what is the breakdown voltage. So you slightly apply lower than your breakdown voltage.
Any other questions for Dollar?
Yeah, one quick comment. And sometimes you also see here, in my case, I get similar value, threshold voltage 0.4 and barrier height 0.4. But in many cases, if you have a lot of non-idealities, either in fabrication or in material, you may see threshold voltage higher. And you may also not see a straight line. You may see a non-linear graph. So then there may be a lot of non-idealities in your case. So that's how also you can claim that whether you have a very ideal device or ideal Schottky diode or not.
So a question for the class, if no one has any questions for Dollar, is I know I haven't given you data to look at a Schottky diode, and I know we had some of those test structures in the mask, but I wasn't able to get data for you. But there is technically a Schottky diode in some of the data that you have. Do you know where that is? Which of the data or which of the devices you would look at to look at a Schottky diode?
We can look at the DHEMT.
Yeah, exactly. So exactly, you would look at the depletion mode HEMT because you have a Schottky metal contact to the AlGaN-GaN structure underneath. And since you have data for a HEMT, a transistor, a 3-terminal device, rather than the two-terminal device that Dollar is showing you on his screen right there, which of the two terminals, or which terminal maybe would you look at to analyze the Schottky behavior? In other words, where would you find the Schottky current, if I can call it that?
Can you repeat the question?
So I guess in the structure that Dollar is showing you here in the slide, he's assuming that you've made a nice two-terminal test structure, a Schottky diode test structure. But you guys only have data for transistors that are 3 terminals. So you have to choose the right terminal to look at in order to find that that Schottky behavior, that Schottky diode behavior. So where would you guys look in a FET data sheet, or not a FET data sheet, a FET data spreadsheet, you know, where the measurement data is collected? Where would you look there to analyze the Schottky diode?
You would look at the junction, or the voltage and current relationship between the gate and the source, I guess.
Yeah, so when you open up the spreadsheet for the FETs, generally speaking, you have 2 different currents, 2 different columns for current, right? And one of them will be your drain current, which is what you are mostly going to be looking at to analyze the performance of the FET. And you're going to use that to find out the threshold voltage and all those other nice things that you care about for a transistor. But for the depletion mode HEMT, or the Schottky gated HEMT, you can look at the gate current relationship with gate voltage applied, and that's basically going to be a Schottky diode behavior. It's a little bit asymmetric, so I wouldn't really call it a good test structure compared to what Dollar's showing you here, where you really have the source and drain, or these 2 ohmic contacts surrounding it. But when you look at the gate current relationship with gate voltage, and you compare it for the D-mode HEMT against your miss HEMT, you should see a very different relationship between gate current and gate voltage. And you should see that for the depletion mode HEMT, you'll have a characteristic that very much resembles the data that Dollar has shown you here for Schottky diode, and it'll look very different for the miss HEMT. I don't want to say too much more because I'll give everything away, but that could potentially be a point of discussion in the reports and something that you think about analyzing.
Yeah, whether you have a better Schottky or not.
Correct, and looking at magnitude of current and how that current changes as a function of the voltage, and how the drain current will also change with respect to how the gate current might be changing. And so maybe to go a little step further, you know, if the gate current starts to approach the same order of magnitude as the drain current, then you know that there's some additional things going on in terms of current flow within the device, right? In an ideal transistor, we usually, a MOSFET, for example, that we assume from silicon, we usually assume that gate current is ideally nothing, and it's only current flowing across the channel. But in a Schottky diode, we know that if you apply a large enough forward voltage, you will get pretty significant current. We just saw that with the exponential relationship. So in D-mode HEMT, you might see something like that as well, and it might impact your drain current behavior as well. So I won't say too much more. I want there to be a little bit of mystery, but hopefully that you know, gives you some hints of what to look at. So if there are no more questions, Dollar, yeah, please continue. This is a good point to keep on going with the
yeah. So I have a room temperature IV and room temperature CV. Let's see how much we can get. I think we have 15 minutes. So I use Origin. I don't know if everyone uses Origin or not, but the main thing I would try to show here is that how to normalize and how to plot and how to extract, probably, if we get more time. Let me minimize this.
Yeah, while that's loading, I just want to comment that I don't expect you guys to use Origin for the assignment. If you're familiar with it, you're more than welcome to use it. But a lot of the things that Dollar will calculate, or you know, the columns he'll create, are columns that you can very much calculate with Excel functions as well. Things like, you know, division and slope and stuff like that. All of those mathematical functions are built into Excel. So it's up to you in which software package you feel more comfortable with.
Yes. So let me plot an IV first. the simplest thing I can do is okay. So when you import the IV graph after the measurement, it looks like this. You have again same different columns, a different sheet, as I think you will see in Excel file. And then because when I did the measurement, I separately applied a forward bias and separately reverse bias. So here is the reverse bias voltage that I applied, and I got some current. And this was the extra sheet, the time when I did the measurement and how long it took, which I don't need. So just to plot that, what I need to do is that I need to arrange some things. So then I can put a voltage in my x-axis and current in the y-axis. And then I don't need this. So instead of that, I can say, okay, I have voltage V and then current is A. So I can either directly plot this and it will give me a linear graph. So that is current. And if I want density, and what I need to do is that I need to do a normalization. So then I can say I have, let's say, current density and then ampere per centimeter square. And then I can have a benefit of writing an equation. So then what I need to do is that I have column B where I have my current divided by the area. That diameter was 25. So I'll do 25 into 25. It's a pi r square and 1e minus 8 because it is in micrometer. So that will give me a current density. And then I can plot now this graph. Then I can have a current density. And it's a same graph as that I have plotted in my slides. Here, the same graph. And then you can do, you can get a slope, or also you can get a threshold voltage. And for that, we need to maybe this screening is creating an issue. Okay, it's not allowing me to change here, but anyway, so the point is that here you can make it, can start this point from 0, and then from there, then you can have a straight line, and that will give you the threshold voltage. And then to do a log scale, let me just stop share because I don't know, there's some issue here. Maybe I'll do again sharing. Okay. But you guys can ask in if you guys have any question in between, so that we can keep talking. Okay.
Dollar, don't feel bad. I also ran into a problem when I was trying to.
Yeah, I think, I don't know, there's some issue.
It also gave me issues. I was trying to change the axes and it just wouldn't work for me. So
no, actually, because previously I was using, I guess, multi-screen, and now I'm using only one screen, so the other screen is not visible. Okay, maybe what I can quickly try is connecting the second screen.
So while Dollar is doing that, do you guys have any other questions, either about his slides or anything else related to the project or plotting, just for a minute or so while he sets up?
Okay, I got it here.
Okay, never mind. Go for it.
Yeah. Okay, so now you can see the screen, right?
Yeah.
So as I was telling, you can do is you can change the axis or you can change the scale, and then it will give you from 0, and then you can have a line which will give you the threshold voltage. And another thing you can do is that you can plot in a log scale. So instead of, let's say, scale here in y-axis, you can have a log, and that will give you the log scale. So this is it, I guess, for IV. The only thing you need to make sure is that when you want to plot either current or current density, you have to scale it. So you should not forget that. And for that, you have to use particular the area of the diode. So that's what for IV. And we can quickly do one thing. We can do CV. And for that, for CV, it's a little bit, when you do the plotting, when you do the measurement with Keithley, it will give you a lot of data. So here you can see that CP is your capacitance, then you have conductance measurement, then your DC voltage that you applied, and then you have your frequency. And we can also do different frequencies, let's say 10 kilohertz, 100 kilohertz, or 1 megahertz. And based on the user functions, it will also give you 1 by c square, and then depth, which is some inbuilt function, so we don't use at all normally. And here I applied positive, and here is the negative that I'm interested to plot right now. So what I do is that I need to do some cleaning. So what I do is that I put this one first, and then I don't need frequency, so I just delete the frequency. And I need this 1 by c square near to my voltage, so I put here, which is 1 by c square. And then I don't need this 2, so I just delete. And instead of there, then I put this 2 here. So at the end, what I have is I have voltage, then 1 by c square, then I have capacitance, and then I have conductance. And this unit is normally Faraday, and this is 1 over ohm, and then 1 by Faraday square. And to factorize this, now I know the radius is 150 square, so then I can do the same thing. Column C divided by area. And then if I want to plot, let's say this is now per centimeter square. And if I still want to make, let's say, nanofaraday, then what I can do is I can do C into 1E9. Oops. Column C. Okay. Then I can have a value in this nanofaraday per centimeter square. And similarly, if I want to do, instead of 1 by c square, I want to do area by c square, then I can do column B into area square 250. So that will give me this, and then now I can plot. Let's say I can plot first capacitance, and then as I'm going very high right now, because previously I plotted only till 1 volt here, but now if I go higher, then looks like this, and there is some non-linearity. We'll see when I plot 1 by c square, which is this. So now you can see the graph is changing. Instead of a straight line, previously I was plotting only till 1, 0 to -1, and now if you go higher, I see different doping, meaning either I have a different doping in my device actually, or maybe I have some traps coming into picture. So yeah, that's what I wanted to show, how to normalize all of this, and when you get data, to make sure you remove unnecessary thing and you only plot which is important. And from this graph also, we can take a from here. So let's say if I want to take a slope, I'll do from a straight line, and then can do analyze a linear fit. Then it will give me a value, let's say 2e13, and using this equation now, the slope, then I can find doping, and so I can have ND using the slope. And to see the intercept now, instead of plotting this, maybe I can plot till only 1 volt, then I can change the axis. Okay, another important thing which I think I didn't say is when you extract the value, you need to make sure that this axis is 0. At that place, you can find the phi b CV, because sometimes people forget, instead of having 0 here, they have either 1, 2, or something. And then when you take when you extract this value, then you may get a wrong value compared to the actual method. So I think, yeah, that's it for me. So if you have any question.
Yeah, anyone have any questions?
I don't have any questions in mind, but I'm glad there's a recording of this. This is a lot of information to absorb at once.
Yeah, me too.
Yeah, absolutely. I mean, it's you know, not part of an exam or anything, so don't worry about having to retain all of it. But I thought that it would be interesting to look at these Schottky diodes in a bit more detail, because they're so important for power, both in silicon carbide and in gallium nitride, and in silicon, of course, as well. And I think most of the time we tend to think a lot about transistors and kind of forget about diodes being such an important part of the ecosystem of devices. And as you guys saw from Dollar's presentation, there's a lot of information you can pull from a diode, both about the interface between the metal and the semiconductor, but also about the semiconductor itself. Like, you can pull out information about doping, the doping concentration inside that diode. You can pull out whether it's uniform or non-uniform, get information about defects. You can also get a gauge maybe of your fabrication processes and how they might be affecting the surface. So it's really quite an interesting device, and oftentimes I think in courses we forget about it. Sorry, my daughter.
And it took me 2 years to learn, so I won't expect you ever understand everything within a day or within a one slide. So yeah, I mean, it's good that we have recording, so that would help you in future.
Absolutely. Yeah, thank you, Dollar. And I also encourage you guys to really use some of this knowledge to, again, look at that gate dependence inside the HEMS and think about whether you can apply some of that analysis to that as well. I think there's some interesting observations you can make if you do that. Cool. Well, it is just after 2:45, so I don't want to keep you guys if you don't have any other questions. Last chance. Anyone have any questions for Dollar? Okay, all right. Well, in that case, I'm going to check Moodle this afternoon and answer questions with regard to the project. A reminder that the report is due, I believe, next Monday at just before midnight. So it is coming up. Make sure that you get started on it and spend time analyzing data and writing the report. And then after all of that assignment is completed, we'll move on to the paper discussion. Next Tuesday, for the lecture, we'll have a combination of, again, like some office hours to discuss the papers that you guys are presenting. And then I'll also talk a little bit more about silicon carbide devices, since I wanted to, excuse me, I wanted to give you guys a little bit more background on silicon carbide that I know from the exam you wanted to hear more about. So that's it for today. And thank you, Dollar. Really, again, thank you. Big thanks for putting it together.
No problem.
Thank you.
Yeah, thank you a lot, Dollar.
Yep. See you.
All right. See you guys. Have a good one.
Bye.
Bye bye.
Bye.